Okay, so let's start. So last class we basically talked about uh, the remaining part of advanced ILP, which is dynamic scheduling. We talked about processors where multiple instructions can be issued, processor where you have different functioning units. And when you have that kind of a scenario, you will face different kinds of hazards, not just the read after write hazard that we used to have in pipelining. We have different types of hazards like write after write, then read after write, of course, and then write after read. So these three hazards also will occur in the case of dynamically scheduled processors. Okay. So, or they also called as you know, dynamic multiple issue processors. Okay. So today we'll start with another small topic on I/O and storage. Again, storage I'll not discuss. It's mostly theory, and I'll give this as a reading assignment for you to go through. I'll not discuss details about this, but I/O some aspects we'll be discussing as part of this particular topic. Okay. Now we have been discussing about the processor design. You understood how the processor can be designed, at least a simple processor. Then you saw how it interacts with memory, with the cache, and how cache interacts with your main memory, and how your main memory interacts with your secondary memory. Okay, so these things we are seeing. But one more very important aspect of any digital system, any processor-based system is the I/O part. Okay, so you still have to interact. The computer still has to interact with people. Okay, so for that you need to have some kind of I/O. So that's the reason, or that's a motivation for understanding some basic concepts related to the I/O. Okay. So as you know, even though you are trying to design a processor, finally you have to interact it. The processor has to interact with humans. Okay, so for this we need input, output, as well as some storage. Okay, so we have discussed about processor interaction with the cache and the interaction with the main memory, and also to some extent interaction with the secondary memory. We have mainly concentrated on this discussion, but of course you have other things. So normally secondary memory is treated as an I/O, and you have a separate I/O controller which will take care of the communication between the processor and the secondary memory. And then you might have some other I/O units like your monitor for viewing, your keyboard for entering, okay, entering information or sending information to the computer. And nowadays, if we talk about mobile devices, we talk about touch, we talk about voice assistants, and so all of that. So all of that is basically a kind of I/O. Okay, and for those, for interacting with I/O, you need something called as an I/O controller, and everything is interconnected with the help of a bus. Okay, so you have a memory and I/O interconnect block which will take care of the communication between the processor and the other parts of the other elements which are connected to the processor. Okay, so we treat a processor and a cache as a separate because they usually sit on a same die. Okay, so most of the times they'll be sitting on the same die. Again, there is a difference between die and chip. I hope you know that. So they'll be sitting on the same die, and then you have these elements which are external. So they are connected with the help of a memory and I/O interconnect, and you have a bus which is connected. So bus exists maybe as will be bus basically exists as part of memory I/O interconnect itself. So it will be shared among all of the elements. The same bus is used for communicating by the monitor or by the keyboard or by your secondary memory with the processor. Okay. So there are some metrics which we talk about when we talk about bus. So one is like performance, so how good it is, and whether it is dependable or not, whether it can be expanded, whether if we add more devices, whether you'll be able to, whether your bus will support adding more devices. Okay, and the cost is also an important parameter, and also the size. Okay, it should not be too high, not too low, and so on. Okay, so these are some of the metrics using which the memory bus will be measured. Okay, so which bus is better? So you will be able to decide based on all of these metrics. Now, I/O devices are one thing that you have to understand is I/O devices are very diverse in nature. Okay, it's no diverse in nature in many ways. Okay, for example, we treat secondary memory also as an I/O. Your keyboard as also an I/O. Can you tell me what would be a major difference between these two? Major difference between these two. What are the differences? Let's not talk about major differences. Let's talk about differences. So your secondary memory is also an IO unit. Your keyboard is also an IO unit. So what is the difference between them? Any idea? Keyboard doesn't have storage. Okay. Formats of data. Okay. You can't physically interact with secondary memory. Okay. So to some, keyboard doesn't have storage. That is correct. Okay. So formats of data. Again, that's I'm not sure whether we can say that, but it can't physically interact with secondary memory. Okay. But again, other differences that we can think of. So one major difference is with respect to the communication speeds. Okay, so that is like one major aspect. So normally, whether the IO interacts with the machine or whether it is interacting with the human is also one of the differentiating factor, and also the speeds. Okay, so normally the secondary memory communication between the processor and secondary memory will happen with large data speeds. Of course, not compared to your cache or main memory, but when the keyboard is pressed or when you are communicating with the human, the speeds will usually be less. Okay. So one differentiating factor is the behavior, whether it is an input, output, or a storage. As somebody mentioned, keyboard does not have a storage. It's just a and keyboard is not an output device. It's just an input device. You use it for inputting some data to the processor, and then you have a partner. Okay. The other differentiating factor is the partner. So whether that particular device, whether it is interacting with the human or whether it is interacting with the machine only. Okay, so that is again another differentiating factor, and the most important differentiating factor is the data rate. Okay, so the peak rate at which the data can be transferred between the IO device and the main memory or the processor is basically data rate here. So normally when we interact with keyboards or when we interact with monitors, the speeds will usually be less. Why do you think that is less? Why do you think the speeds with which your keyboard send the information or your monitor displays information is very less? Why is that? Is it that we can't design a fast uh, monitor, a monitor which can refresh at a very high rate? Can't we design that? That it has to go through external bus, okay. But again, secondary memory also goes through an external bus, right? But secondary memory works at a higher speeds when compared to your monitor or a keyboard. It's not required beyond a certain speed. Why is that? Because as earlier Rahul had said, it's because of the limitation of humans. Okay, we are not as fast as the machine. Okay, because again, as somebody has pointed out, because of our limitations of vision, we have limitations of our the rate at which we type. Okay, so humans are limited with respect to the speeds with which they can operate. So hence, you will be able to even if it works at lower speeds, it's fine. Okay, so that's the reason you'll have different data rates when you're interacting with either human or a machine. Okay, so this is just giving you an idea about the typical data rates that will exist. Okay, so normally your keyboard, where you have a partner as human, which is an input device, you will have 0.0001 Mbps as the speed. Okay, so this is bits per second. And mouse a little bit faster. The hand movement is a little bit faster than typing. Of course, here you have a slightly higher speeds. And if you see, the speeds will grow. There is a very large difference in order of magnitude. Okay, so this is 0.0001, and the magnet disk, which is your secondary memory. So where the partner is a machine, it has a very high speed. Okay, so it is 2560 Mbps. Again, I'm not comparing it with a cache and telling you this is having high speed. With respect to the other IO devices, it has high speeds, and your LAN also is in the range of 1000 and mega bits per second and so on. So what I'm trying to say is you have to understand that all of these are typically connected to a single bus, and your bus should be such that it can support all of these different kinds of devices with different speeds. So the same bus is used to communicate with the magnetic disk, which has very high data rate, but the same bus is used to communicate with the keyboard, which has a very low data rate. So your bus should be able to support all of these different types of devices with different types of properties. Okay, so that's one thing that you have to understand. Okay, so there are two things with respect to I/O. One is called as I/O bandwidth, which we call it as throughput, and then there is something called as response time. Okay, so which is again called as latency. So many applications require both high throughput and short response time, but again, majority of them will require either high throughput or very high response time. Okay, so coming to the bus. So what do you understand by a bus? Okay, so what do you understand by a bus? You have already done the microprocessor course, and you have already uh, understood some aspects of computer architecture. So what do you understand by a bus? It's an array of wires. Okay, that is just a very fun, very basic definition. But beyond that, so if I connect, can I say the electrical connection? You see, you connect your what do you say? Maybe some device to electricity, let's say, and if they are also bunch of wires, can I call them as a bus? An array of wires, can I call always a bus? Again, if you're talking with respect to Verilog, of course that is correct. But if I take a bunch of wires, can I call it as a bus? What property should a bus have? An electrical connection that can carry more than one bit at a time still not correspond to the same data. Mm, Still, it's like you're close, but maybe not the correct answer. When you say bus, what thing? It's not just group of wires, right? The connection between should be between computer components. Uh, Again, that's also true, but can I just take a group of wires which are communicating between two devices and can I call it as a bus? Or do you think something extra should be there? So whenever there is a bus, there is always something attached to it. Means of data transfer within the computer. Of course, that is correct. But there is always something additional attached with the connections. It's not just a group of wires or a group of data lines connected between two things. That's not a bus. Okay, so bus, one more very important property of a bus is that they work on some rules, okay, which we generally call it as protocols. Okay, so bus is a shared communication link that needs to support a range of devices with wide variety of data rates and latencies. That's one thing, and they should work on some understanding. Okay, so there are many protocols that are used to make sure that the communication happens properly. It's not just communication between two devices. There will be some controller which will take care of how the communication happens. Okay, so there should be a basic protocol could be an handshaking protocol. So whenever two things are connected, the master will first send some signal to the slave saying, "Are you ready?" Then the slave will send a signal saying, "Yes, I am." Then the master will send me the data. Then the slave will send the data, and the master will send an acknowledgement saying that I have received the data, and then the IO will know that the data has been received, or the slave has been received. The slave will know that the data has been received by the master. So some kind of rules should be there. It's not just connection. It's connection of wires with where the communication happens based on certain rules. So that is what we call it as a bus. And the advantage of a bus is it's versatile. It's like versatile because it supports a lot of different types of devices and it is low cost. Disadvantages, it will create a communication bottleneck. So this is compared, let's say it's like having a processor, and instead of connecting different devices directly to the processor, they are connecting processor to a bus, and then there will be a bus controller, and that will take care of communication between different board devices. So this is also one type of communication, right? So here also you can connect devices directly to the processor. So, but here the cost will be very high. And here the problem is the same bus is being used for all devices, so that will create a communication bottleneck. So this advantage and disadvantages between these two type of these two different types of organizations, where each IO has a separate dedicated data line, but here you have a common bus which will take care of the communication between different IO and the processor. Okay. So when you have this kind of a scenario, the communication bottleneck will be less because each IO will have its own data lines where it can keep on sending and receiving the data. But here you have a common bus which will communicate with the processor, and all IOs have to use the same bus. So that way it will create some kind of communication bottleneck. Okay. So the maximum speed of the particular bus is limited by its length, the length of the connection, and also the different devices that are on it. So coming to the bus characteristics, so a bus can be grouped into two parts. Okay, it's not just data, as I said, right? It's not just data lines. It also has some lines for having a correct communication. Okay, so which is called as control lines. Okay, so normally you have a bus master. Most of the times this will be a processor, and bus slave, which is most of the times the IO or another unit which is connected to the processor. And usually master initiates request, and the data can go either way. The data can be sent from master to the slave or from slave to the master. Okay. So bus transaction basically consists of master issuing a command, maybe an address. So this is a request, and then the slave receiving or sending the data. So that is called as action. So a bus transaction or a bus communication is basically combination of two things. So one is sending a request, and then action taking place based on that particular request. So there are different types of buses. So some are generic in nature, some are specific to companies. Okay, so which is proprietary. So for example, the processor memory bus, meaning your processor and your main memory bus. Okay, so this bus is proprietary. Okay, so many companies have their own names for it. But when it comes to IO bus, okay, when it comes to IO bus where you connect your secondary memory, or you connect your monitor, or you connect your keyboard. So for all of that, you have some industry standards like USB, you have SCSI, FireWire, and so on. Okay, UART. So all of that will be basically used as your IO bus. Okay, so one thing you have to understand is this processor memory bus is proprietary. So different companies will have their own internal architecture, bus architecture for communication between processor and main memory, because this is time critical in nature. Okay, so they'll have their own optimizations based on the processor model and based on your main memory. But here you have IO bus, which is generic in nature, because IO, it's not the processor companies which supply the IO. There are many third parties which supply the IOs. So you need to have industry standards so that different companies can produce different devices which satisfy the criteria for that particular IO. Okay, and then there is something called as a backplane bus, which I will talk about later, which is basically a communication between these two units. So there is a bus which can communicate between these two. So that is called as backplane bus. So processor memory bus is typically short, very high speed, and it is optimized for cache block transfers, because you need to transfer blocks from your main memory to cache. So this is mainly optimized for that. So IO bus is typically lengthy, slower, and this has to support wide variety of IOs. Okay, so if you have used desktops, you know that there used to be separate slots where you actually insert a another chip, another, they used to call it as cards, which support either the keyboard or either the monitor, or separate slot for fixing uh, your extra GPU and so on. Okay, so all of that were basically communicating through the IO bus. And then you have backplane bus, which is basically an intermediary bus which connect the IO bus with the processor memory bus. Okay, so there will be an interconnection between them. They are not independent of each other. So there will be some kind of interconnection connection between the processor memory bus and the IO bus. So that they call it as backplane bus. Again, there is an industry standard for this. It's not proprietary and which is not separate for each one. So when it comes to IO bus transaction, sending the address and receiving the data. So in an input operation, what happens? You input the data from IO device to the processor, and output operation is one where you output the data from processor to the IO device. Okay, so this is called an input operation. This is called as an output operation. Typically, what kind of instructions are used to have this kind of communication? So when I say I want to input data from IO device to memory or a processor, okay, memory processor are considered to be a single unit here. Okay, if I want to send some data from input to the uh, some input device to the processor, what kind of, you need some instructions to support it, right? No, not just interrupts. Instructions. I'm talking about instructions. So in 8086, you would have studied these instructions. Any idea? Again, yeah, here you have to ask me one question. Based on that question only, you'll be able to understand what instructions are used. So how is IO treated as? Is it separate unit, or do you consider it as something else? So have you heard about memory mapped IO and IO mapped IO? Again, these are all basics. It is supposed to be taught as part of microprocessor course. I'm not sure how much you know about it. Memory mapped IO and IO mapped IO. Anybody has any idea what this means? Memory mapped IO and IO mapped IO? Yes or no? If no, then I'll quickly explain. Okay, so memory mapped IO, what happens in memory mapped IO is the IO devices are treated as memory. Okay, are treated as memory. Here IO are treated as separate entities. Okay, so here the IO devices will be mapped to some memory locations. Okay, so here IO will be mapped to some memory locations. Okay, here it will not be that. It will be separate entity altogether. So if you want to communicate with IO in the memory mapped IO, they use normal instructions which communicate with memory. So they'll assume that some 5,000 address to 6,000 address, I am dedicating it for IO devices. So this entire range of memory, I am dedicating it for IO devices. That is assumed. And if you want to access data from this memory or send data to this particular IO or receive data from this particular IO, they use normal instructions. In 8086, you would have used move instructions only. Move AX, comma 5000. If you say, so some data will be moved to some IO block which is mapped to this address. Okay. And similarly, if you want to receive the data, you do, sorry, this is receiving the data. If you want to send the data, you do the other way. So here you will be sending the data in AX to IO, which is there, which is mapped to 5000 location. So this is how you communicate with IO in the case of memory mapped IO. Okay. In the case of IO mapped IO, how do you think the communication happens? I think in lab you might have used some of these things. So in IO mapped IO, do you know any instructions which can communicate with IO units? So here, if your IO is assumed to be mapped to some memory address, you use normal instructions like move move your register and memory location. And again, you want to send the data, receive the data from IO, you use this instruction. If you want to send the data to the IO unit, you use this instruction. But here, do you know any instructions? I think this at least you should be able to tell. Do you know any instructions which can communicate with no interrupts, not interrupts? So there is something called as in and out instructions, right? You don't know this in 8086? You remember? Not you don't remember, or you have not learned only? We did it very briefly. Okay. We never did interfacing. Oh, okay. Okay, so in and out instructions will be used. Okay, so okay, maybe due to some issues you are not able to do, but you should have the idea. So some processors use memory mapped IO, some processor will use IO mapped IO, and in that case they use instructions like in and out. So in is basically you take the input from the IO device, out is basically you send the data from processor and send it as output to your IO device. Okay, so this is how you communicate with the. These are separate instructions. If you search for these instructions in 8086, you will get. Okay, you get to know that. If you have done at least embedded system design, this is how you can communicate with the different ports of a microcontroller. Okay, so you have instructions like in and out, which will communicate with the memory. That's the difference between memory mapped IO and IO mapped IO. Memory mapped IO, your IO device is assumed to be mapped to some address. In IO mapped IO, your IO are treated as separate entity and use separate instructions to communicate with those. Okay. So that was about your operation. And the one more important thing is basically your interconnect, your memory and IO interconnect. So we typically use, as I said, standard bus protocols like USB, PCI, SATA for the communication with the different IO devices. So a few things about these buses. So traditional buses were synchronous. Even today's processor memory bus is still synchronous. The communication link between the processor and the memory is still synchronous in nature, meaning it will depend on the clock. Okay, so it's related to clock and easy to implement, and this is fast. And every device should have a same clock. Okay, so that is basically what we mean by synchronous. But again, due to the long nature of the bus, you might have clock skew problems. Clock skew is again, if you have two devices and this is the clock source, okay, both the devices will not receive the clock at the same time. If this is your clock, if this is your clock A and this is your clock B, due to the delay for the connections, if this is your original clock, which is starting at, let's say, time t, the clock A, which is received on device A, might be slightly delayed, okay, because of the delay of the interconnection. Okay, so this difference they call it as clock skew. Okay, so when you have clock skew, it will create a problem with respect to timing violations. So again, it's basically what was one of the disadvantages of having a long bus. Okay, today's buses are mostly asynchronous in nature, except for this particular thing. Except for processor memory, all your IO buses are asynchronous in nature, so it's no restriction on the clock period. So you can have lengthy buses, but the implementation is a little bit complex. Okay, so if they are not relative to clock, then you have to have some other mechanism so that there is some kind of communication happening between the processor and the IO. Okay, so the implementation will be a little bit complex. And as I said, you use something called as handshaking protocols to effectively communicate between for effective communication to happen between a processor and IO. You need some kind of protocols because there is no clock here. That's the reason you need some kind of mechanism to synchronize. So that will be typically done with the help of handshaking. Okay, so again, this is just giving an idea about the entire thing that I talked about. So typically, you have one of the buses which will interact with the processor and the main memory. So this is typically synchronous in nature, and this is proprietary. Okay, and then you have another bus which is interacting with IO devices. Okay, so and this communication is basically your backplane bus that I talked about. So here they use general protocols like like PCI, SATA, or you have USB, UART. So all of those bus protocols will be used for communication here. Okay, so in Intel processors, they have different terminology. They call this as North Bridge, the bus which communicates between the processor and the main memory. They call it as North Bridge, and this they call it as South Bridge. Okay, the bus which communicates between IO devices and the processor, at least not directly through this particular controller. So that they call it as South Bridge. So here you see that the speeds are very much different. So here you have a SATA which has a speed of 300 MB per second, and then you have a PCI, which is 1 GB per second, and then you have a parallel USB, which is 60 MB per second. So different speeds are supported here. Okay, but here and which are slower, much slower. But when you compare it with these, so these are much faster. So here you deal with uh, uh, gigabytes per second kind of speeds. Okay, and then if you want to, this Northbridge is also called as a DMA controller because without interaction of a processor, the data can be sent from your main memory to IO device or from IO device to your main memory. Okay, so whenever we talked about page fault, right? So this is like one of the scenarios, right? So there has to be some data which is sent from the disk to the main memory. So that happens through this. But sometimes if you want to move large chunks of data, the processor can just send the starting address and the ending address, and the communication can keep on happening while the processor executes other instructions. So that is what is your DMA controller. So DMA controller is basically used to move large chunks of data from your IO device, which can be either your secondary memory or some other IO unit, to your main memory without the involvement of the processor. Okay. So this DMA controller will be helpful when you want to move large chunks of data, and the processor need not be involved in each of the communication. Okay. So whenever you have such a communication where there are many devices connected, okay, so you need some kind of arbitration. Okay, what do you mean by arbitration is, so let's say this disk is requesting the data and there is some other IO which is also requesting the data from the processor. In that case, there will be some kind of mechanism to choose which request to be taken first. Should I take the request coming from the disk, or should I take the request coming from some other IO unit? So that is where you have something called as bus arbitration. So multiple devices may need to use the bus at the same time. So you must have a way to arbitrate multiple requests. Okay, so based on some kind of mechanism, you keep allotting the bus to a particular IO device. Okay, so bus arbitration schemes, there are many arbitration schemes. So they should try to balance two things. So one is called as bus priority, meaning the highest priority device should be serviced first. Okay, so that is what is meant by maintaining bus priority. But then there is another thing also that is important. The other thing is fairness. So even the lowest priority device should never be completely locked out from the bus. Okay, so there are many devices, and some will have some higher priority, some will have lowest priority. For example, if there is a page fault and if there is a keyboard key that is getting pressed, obviously the preference will be given to the secondary memory and rather than your keyboard. So that is usually the secondary memory might have a little more higher priority when compared with keyboard. So, but then the keyboard should still get access. If not earlier, even if it is late, it is fine. But it still should get access. It should not get completely locked out from the bus. Okay, so that is what we call it as fairness. Okay, so even the lowest priority device should still be able to access the bus. It should not be completely locked out. So that is basically fairness. And then priority. So based on the priority, some devices should get higher priority when compared to others. So based on this, so there are many arbitration schemes that that are available. So we'll be discussing maybe a couple of them in detail. So one is called as daisy chain arbitration. So one of the examples that is typically this arbitration scheme is used is called as mu bus protocol. So the architecture will look something like this. So you have a controller which is connected to the processor. So this is your main control unit, which will decide which device should get the priority for the bus. Okay, so which device should get access to the bus. Okay, so here what happens is you keep sending the request. So the device one will send the request, device two, and so on. So there will be a request sent by the devices, IO devices, and based on that, the bus arbiter will now have to check which device has requested for the data or which device has requested for bus access. Okay, so for that, what it does, it sends the acknowledgement to first the highest priority device, see if it has requested it. Okay, it's like an and of all of these signals. So let's say this has requested, so this has not requested and this has not requested. Okay, so what happens in this case? So this will be one. It's like and of all, sorry, or of all of these things. So this will be one. So when it sees that there is a one on request signal, it will send an acknowledgement to check which device has actually requested for the bus access. So it will send an acknowledgement signal to the device which has the highest priority. This device will tell whether it has requested the data or not. If it has not requested, it will say I have not requested the data or I have not requested the for the bus access. Then it will send the acknowledgement to the next device. Okay. And when it goes to the next device, so again here you check whether this device has requested for the bus access or not, and so on. So this way, the acknowledgement signal goes through different devices, and then it will reach the lowest priority device. So now can you tell me what are the advantages and disadvantages of this architecture? What is the advantage and what is the disadvantage of this kind of architecture? Now, two things you have to look at. Okay, one is priority, the other one is fairness. So do you think this architecture is fair? You understood what is fairness, right? So high priority devices are getting serviced quickly. Okay, that is correct. But it's not fair. Why is it not fair? And again, the other disadvantage is if the last request device is requesting for the bus access, the acknowledgement signal has to propagate through all the devices. So that is that is like it will take more time. So one more disadvantage, it's not fair. Okay, so advantage is simple to implement. Disadvantage is it can't assure fairness because if first time the second device requested for the access, even though let's say it is requesting the access, this is also requesting the access, so this will not get serviced. Next time, let's say device 3 requests access, then this will not get a service. So this way, the lowest priority device might never get access to the data bus, which is not fair. Okay, so it can't assure fairness because the low priority device may be locked out indefinitely because the devices which have slightly higher priority can keep on requesting the bus. Okay, so that way this might not get access. This might not get access to the bus. So it's not very fair. It's slower. The reason it is slower is the acknowledgement signal has to propagate through all of the devices, and the grant signal. This due to this, the speed of the bus will be limited. Okay. So this is like one of the arbitration schemes, which they call it as daisy chain architecture. So then you have another architecture which is called as centralized parallel arbitration scheme, where each device has its own acknowledgement signal. So the bus arbitrator based on which device and separate request signals. So first it will check all the request signals coming from all of the devices, and based on which signal, which device is requesting for the bus or for the data. So the bus access will be given to that particular device with the help of an acknowledgement. Okay, and then later the communication can happen with respect to data and address bus. Okay, so can you tell me advantages and disadvantages of this? What is the advantage and disadvantage of this? It is fair, but disadvantage. Priority can also be done. The major problem here is what? So later the bus arbiter, after seeing that a particular devices are low priority device has requested for the bus, after so many requests coming from higher priority devices, it still might give access to a low priority device after some time. Okay, so that way fairness can be maintained. But the problem is the implementation is complex. If you see there are a lot of acknowledgement signals, there are a lot of request signals that are available. The bus arbiter should be implemented in a very complex way to implement. It's like flexible. It can assure fairness. Okay, but the disadvantage is it will have a very complicated hardware in the bus arbiter. Okay, and it's usually used in all processor memory buses and high speed IO buses. So since the speed is very high here, so whenever you want to communicate with high speed devices, you go with this particular architecture. But again, as you know, the architecture is a bit complex here. Okay, so then you have other schemes also. So one is called as distributed arbitration by self selection. So here the devices requesting the bus decide who will be granted access. So here the control sits in the arbiter. Okay, but here the arbiter work is distributed among the devices. Okay, so there will be some controller which is communicating with the devices, and the devices will decide which other device should get the access. Okay, so it's slightly tricky, but again, you don't have to go into the architecture details. So you just have to understand how it works. Okay, so devices requesting the bus will decide who will be granted access. So devices, what they'll do is they'll send a code along with the request. It will send a code. Okay, that code will indicate basically the priority. And whenever, for example, you have a device one and you have a device two. Okay, so both will send their priority numbers and a request. So this is your request signal. This is a priority. Let's say one is the highest priority and two is the lowest priority. So whenever it's sending the request, so whenever it's this particular device, whenever this particular device sees that there is another device which is requesting for the bus and that has the highest priority, what will this device do? This will cancel its request. Okay, it will cancel its request. So there it was done by the hardware. Here the device itself is doing it. Okay, the device itself, by seeing that there is another device which is requesting for the bus and the priority of that is higher, it will cancel its request. Okay, so low priority device will leave the bus if it notices a high priority requester. Okay, so it's called as distributed arbitration because the arbitration is not centralized; it is distributed among the devices itself. Okay, and it is based on self-selection. Okay, so based on self-selection, this device itself is deciding whether I should cancel my request or not based on the other devices that are requesting the data. Hence, we say that this is arbitration by self-selection. There is another similar scheme which is called as distributed arbitration by collision. So here devices independently request the bus and I'll assume access. But whenever there are simultaneous requests, okay, it will result in a collision. Okay, so for example, you have just the same example. So you have device one, device two. So it will send for request. It will send for request. Okay. Now both the devices are sending the request for the bus, so there will be collision. So now this collision is resolved. Okay, so with the help of some kind of algorithm, okay, some kind of scheme to identify which device should be given the access. It's not just based on priority. This scheme that is used to select colliding parties, one of the colliding parties might be a little more complicated than just the priority. Maybe some kind of a scheme where you don't give access to the device which has recently accessed the bus. You give it to a device which has not accessed the bus for a very long time. So that way some scheme can be developed. So that's the difference between self-selection and the collision. In self-selection, the device, when it sees a higher priority device, it will itself stop the request. But here it will send the request. There will be another scheme. There will be another controller maybe which will decide which device should be given a priority whenever there is a collision. So that scheme might not be a simple priority based. It might be a bit complex in nature. Okay. So this is about the bus and the arbitration schemes and so on. But one thing that you have to understand is you have to understand how the processor actually accesses the IOs. Okay, so if the data is sent to the IO device, to which address does the processor send it to? Okay, so this is what I talked about. Okay, there are two things. So one is called as memory mapped IO, where portions of the memory addresses are assigned to IO devices. Okay, so if you remember the address decoding part, so the address, whenever you wanted to access memory, so some address was allocated to IO devices or some other external devices. So that was basically your memory mapped IO. Okay, and you interact with the help of move instructions. This is example for 8086. So if you are talking about maybe MIPS or RISC-V, you communicate with the memory using load store instructions. So these instructions would be used for interacting with IOs if some address is assigned to IO devices. Then there is something called as IO mapped IO, where there is a separate access for IO devices. So for example, you use instructions like out, and then you specify the address of the port of that particular IO. Okay, and you might interact with some registers only, so that register will be mentioned. Okay, so this is some example of memory mapped IO and IO mapped IO. So this is how the processor actually communicates with IO devices. The processor will keep executing only the instructions, right? It does not have any idea about if there is a bus arbiter, if there is a arbitration scheme going on. It will just want to send and receive the data with respect to IO units. So that communication will happen through one of these instructions based on what kind of architecture is followed. Now, if this is how the communication happens, but how do you know how does the processor know whether IO is requesting the data or not? So how does the processor know whether IO request is whether the IO is requesting the data or not? So when there are two different IO devices, so that will be resolved at the bus arbiter. Okay, and then the request will be sent to the processor. But where will the processor receive that request? How does the processor know if the IO is requesting for some data or whether it needs to? Is it always with respect to using interrupts? Is interrupts the only scheme? You have many schemes, right? It's not just interrupts. So one of the simplest scheme is polling. Okay, so you in the processor, what you do, you keep checking the IO port. Okay, so you periodically check for whether IO requires attention, whether IO is requiring some data or not. Okay, so but there is a lot of time wasted in checking for that. The processor has many other tasks to do, many other instructions to execute. So this is not preferred very much. So this is called as polling. The other one, as many of you have pointed out, it is through an interrupt signal. So whenever IO wants some data from the processor or it needs to send some data to the processor, it will raise an interrupt. So IO sends an interrupt to the processor, and based on that, uh, some some task is done, which can send the data to the processor or receive the data from it. So interrupt will have again priority levels. You have, I hope you know these concepts. So interrupts, if there are many interrupt pins, so you should have some kind of priority between different types of interrupts. And in some cases, you might have to mask some of the interrupts. So that should also be allowed. So interrupt priority level should be there, and also interrupt masking should be allowed whenever you have this kind of a, architecture. Okay. So this is best for lower priority. This interrupt-based thing is best for lower bandwidth devices. Okay. So sometimes the IO might request the processor to move large amounts of data, okay, from memory to the IO. So in this case, you know that we'll be using something called as DMA. Okay. So here interrupt might still be used to initiate the first transfer or on some error or on some completion, but during the actual data movement, neither the processor will be communicating with the IO. The processor will be doing its own execution of other instructions. Okay. Normally, DMA does not go through the TLB and cache, because we are saying that processor, TLB and cache are on the same die typically. And then your main memory is something which is separate. So whenever IO communication between IO and memory happens, so it has to happen independently with the help of a DMA controller. But what is the advantage if it does not interact with TLB and cache? Can you tell me what kind of problem might arise? Any idea? What kind of problem might arise if DMA does not go through the TLB and cache? It results in difficulties. Can anybody guess what would be the difficulty? What would be the problem? Because the processor will be working, will still be executing some instructions. Okay, yeah. What if the cache is dirty? Okay, so let me give an example for that. So what difficulties you will face? So let's assume that the processor wants to read X. Okay, so if the processor wants to read from some X location, so let's say X is initially 4, it results in a, let's assume it results in a cache miss. So this X is equal to 4 will now be available in the cache. Now at this point, let's say, and then the 4 will be sent to the processor. So at this point, if let's say the processor writes into X a value of 5, and let's assume it will get updated in the cache, but it is following a write back scheme. Now, if it is following a write back scheme, what do you mean by that? What do you mean by it follows a write back scheme? What do you mean by that? It'll only change the cache. Will it change the main memory at this point? So assuming that this is still available in the cache and it is not replaced, it will not be updated to the main memory. The main memory will have a value, old value, which is 4. Now at this point, there is a DMA access that's initiating the data transfer between some IO and main memory, and it is requesting for some data which is X. So it will see a wrong value of X, which is 4 here. Okay, so normally it should see a correct value of X, which is 5. Okay, but here it is seeing a wrong value of 4. So this problem will be there. So in this case, can you tell me how do you resolve this? Any ideas on how to resolve this? Okay, you understand the problem, right? So it is only updated in the cache and it's not updated in the main memory. And at that time, if there is a transfer with the help of DMA, so DMA might initiate transfer between main memory and IO controller. So in that, cache will not be involved. So it will create a problem. So there are some ways to resolve the problem. So it's called as cache coherence problem. So what you do is you either route all IO activity through the cache. That is one solution. But it's very expensive and it have a negative performance impact, because once you want to do involve cache, then the processor might not be able to access the cache at that time. So it'll impact in a negative way. So this is not the right way to go. So what you can do is the OS can do a few things here. The OS can invalidate few locations on IO read, and it might force write back on a IO write. For example, so in this case, if there is some writing to the IO, meaning you are supposed to send this data to the IO controller. So when it's supposed to send this data to the IO controller, which we are stating it as IO write, okay, because I'm writing into some IO device. At this point, even though this block is not getting replaced, you force write into the main memory. Okay, understood? So whenever you see that a particular address X, okay, is supposed to be sent to the IO, so instead of taking the old value, you first write back, even though this block is not getting replaced. Okay, so we usually write back only when this block is about to be replaced. But here in this case, we have to forcefully write into the main memory and then only send the correct data. So that is how you will be able to rectify this error. The other problem is, so here you have X is equal to 5 currently, and IO read operation, meaning you read something from IO which is to be updated. Now IO wants to write in location X a 6 value. So in this case, if the processor is requesting the X data, it will read 5 instead of reading 6, which is wrong because IO has modified that data. So at this point also, whenever IO read happens, okay, whenever you are trying to read from IO and write into the main memory, at this point, what you have to do is you have to invalidate this. Okay, invalidate this. What do you mean by invalidate this? The corresponding location will be having a valid bit to be equal to 0. It basically says that the location in the cache will have wrong data. First, you take the data from your main memory, put it in the cache, and then only send it to the processor. Okay, so that's how it will be done with respect to the DMA-based communication. Okay, so that's what it is being sent here. Whenever there is IO read, meaning something is read from the IO and written to the main memory, you have to invalidate cache block. Okay, and whenever you are trying to write into the IO, meaning you are reading from main memory, and then at that point you have to basically force write back. Okay, you have to forcefully write back the data that is available in the cache into the main memory, and then only go ahead. Okay. So this is how the DMA access the cache coherence problem in DMA is resolved. Okay, so you need to provide hardware to selectively invalidate or flush the cache with the help of a snooper, because you need to constantly check which addresses are being accessed by the DMA. So there will be a hardware unit which will constantly snoop what addresses are being accessed by the IO, and based on that, it will either forcefully write back or it will forcefully invalidate the data that is available in the cache. Okay, so that is how the cache coherence problem with respect to DMA is resolved. Okay, so again, last but not least, operating system has a very important part to play because it acts as an interface between your I/O hardware and the program that is requesting the I/O. So your OS must be able to give commands to the I/O devices. It will be able to handle interrupts, and it will be able to provide access to the shared I/O resources and schedule I/O request to enhance the system throughput. Okay, so it basically means that it's not just hardware and I/O devices on the bus. It's also there is a big involvement of OS and there is communication between the I/O devices. I think with that, this I/O related topic is done. Okay, so there is the storage concepts which talk about many things. I think that I'll give it as a reading assignment. Okay, so we can go through these particular topics. So you have to read through these topics for understanding the storage concepts. Okay, it will mostly be theory, not very much conceptual. It basically talks about how the disk storage is organized, what is the RAID. It talks about flash storage, implementations, and so on. So for our course, it's not very much relevant, at least as a architecture course. So I think you can go through it on your own. If you have any doubts with respect to the topics that I discussed today, you can clarify them. Otherwise, that's all from my side. Thank you. Okay, so there is one more lecture on the multi-core processors and cache coherence that I'll be taking on Monday. Okay, so we'll discuss about what to do for the next 3 classes, maybe in the next class. Yeah, so if you have any doubts related to any of the topics that I discussed, please let me know. Thank you.
Sir?
Yeah.
Sir, actually, I submitted my assignment yesterday.
Okay.
So like